Now let's find the magnetic field from a solenoid. There's another video out there where I find it from a single loop, and that I will make a reference to that within this with what the preliminary title is. So I am going to make an assumption here that the solenoid, the loops are tightly wound. There's no gap between the wires, and also that the thickness of the coil is constant. So basically, in essence, I'm assuming that they're squared off as opposed to circular, where we do have some gaps right there. But I'm assuming the uniform coil density and that the coil density is constant, which goes along very much with the uniform coil density. So if I take a look at my coils right here of length L, a radius of big R, and I have a current flowing through it, I basically chop off a cross section right there, and this is what I'm looking at here. So I have the current coming out this way and in that way, so my current is flowing around like this. And my magnetic field is going to be in that direction. You can use the right-hand rule and ultimately come up with that. So I'm going to let IT be the total current running through a cross-section that encompasses all of the coils. So if I take a look at all of this, I have current flowing through here, here, here. Each of these wires is producing a total current. I'm going to let capital N be the number of coils, and little n be the coil density. In other words, the number of coils divided by that length of it. Same as we used in another video, except I might have used a lowercase l in that one. So dn dy, so if I think about a sort of the y-axis along that way, and I hat, j hat, k hat as defined right there, that the coil density, since it's uniform, the total coil density should be equal to the coil density at any particular spot right there. So dn dy. So since the total current would be the current flowing through the wire times the number of coils, so the N, capital N, is the number of basically these X's or those dots. Since the coil density is big N over L, big N is also equal to the coil density times L. So that's the substitution we have right there. And we just put it in a slightly different order. So dit is, well, take the derivative of it. The current here is constant, the coil density is constant, and so dit is just equal to Ni dy. And then we can go ahead and put the other substitution back of what coil density is. Probably an extra step in there, but still all legitimate math. So now let's take a look. I got my wires right here with the current flowing into the page all along there and out of the page all along here. And I'm looking at some spot, a distance of negative d from there. In this notation here, d is the distance from one end of the solenoid to the point on the central axis. Positive value of d would be out here. Negative value of d would be inside there. And I want to find the magnetic field at some point inside. We could pick one outside as well. The math pretty much holds. So if d is less than 0, if within the solenoid, and greater than 0 if outside the solenoid. Now we're going to consider a loop of width dy. So I'm looking at a dy right there at a point of y plus d. So this distance from here to here is y. The distance from here to here is negative d. And so the distance from here to here would be y minus negative d. So this distance, y minus negative d, which is y plus d. And so using the video, which has B field from a loop of current along the axis, that's the tentative title, and I hope I remember to actually call it that. This was the formula from that, where this was the distance from that loop. And so applying this specific case, that'd be y plus d. Now, there are I hat components and k hat components, but they would all cancel out because of symmetry arguments. So again, we'll be left with, since I'm along the central axis here, is this j hat. So all I did was just shift things around here. I'm going to do some u substitution, let u equal y plus d, so du equals dy. So the integral from 0 to L of dy would be the integral from capital D to L plus d du. And so now we solve for b. We integrate both sides. We get b on the left, and on the right-hand side we have a definite integral. And this is an integral that has shown up several times, and you just look it up somewhere, or you can do, I think it's a trig substitution, but it's simplest just to look it up, and we end up with, that's the integral from big D to L plus D. And so the magnetic field once you do the substitution, you get that. And in pretty much the same form as what I had before. Oh, the only difference between this and this is I put in the coil density back again as opposed to the number of coils and the length. Whichever one. There's a lab that we do where this is the formula that's presented. So that's the generalized formula for the magnetic field along the solenoid. So I have a solenoid like this. I have one end of it right here, and we have a distance negative d from the end. The magnetic field at that value from the solenoid is expressed by this. Now, if we take a look at what about in the middle, or if L is incredibly huge, do we get the same answer as is typically derived in a physics class? And yes, we will. So let's work through it. So basically it's the same thing, except I'm factoring out an L plus D squared and a D squared. So I end up with this. So because I'm factoring out L plus D squared, square root of that, I get L plus D here, and I get a negative D here. And this is the tricky spot right here, that the square root of D squared is the absolute value of D, but D is a negative number. And so when I factor it out, I get negative D. So we end up with mu naught little n I over 2. And again, this current, that is not the total current running through my loop, but that is the current that is going through the wire. And the L plus D's cancel out, the D's cancel out, so I'm left with this. If L over 2 is much bigger than R, so we're dealing with a length, that's L, and this is R. If L is much larger than R, or I specifically did if L over 2 is much larger than R, then I'm choosing that because that's the middle of the solenoid where D is equal to negative L over 2. Then R over L plus D squared is roughly equal to R over L over 2 squared, which is approximately equal to 0. In other words, this term and this term go off to 0, and we end up with j hat mu naught little n I over 2 times 1 plus 1, which is j hat mu naught n I. This is the equation that we derived in using the Ampere's law to find the B field inside a solenoid. So that is the specific case for the ideal solenoid, infinitely long, and this is the slightly less ideal. This is a finite length solenoid. And that should be it.